Today, we're going to take a look at a famous piece of algebra. But we're not going to do it with a bunch of symbols and equations. Nope, we're going to try to actually see it, to understand its physical shape. Let's dive in.
I'm betting this looks pretty familiar. It's one of those first big algebraic rules we all had to learn, right? The square of a sum equals the square of the first, plus twice the product of the two, plus the square of the second. And let's be real, for most of us, that's exactly what we did. We memorized it. We ran drills, we repeated it over and over, we plugged it into problems. It was just this string of symbols that, worked.
But did you ever stop and think about what it actually means? What does a plus b squared really look like? Well, that's the big question for today. We're going to move past the symbols and find something we can actually picture.
Okay, so let's start at the most basic place possible. A simple line, just one dimension. In one dimension, a plus b isn't some complex idea. It's just a length. You picture a little segment of length a, and you stick a segment of length b right next to it, the total length, it's just a plus b. Super simple. This is our foundation.
All right, now let's take that one-dimensional line and jump up to 2 dimensions, because this is where the formula really starts to come alive.
So if a plus b is a length, then it makes sense that a plus b squared would be, well, the area of a square with sides of that exact length. And check this out. It perfectly illustrates the formula. You can see the whole area is just one big square, but it's made up of these smaller, distinct pieces.
And what are those 4 pieces? Well, you've got one square that's a by a. That's our a squared. Then you have another smaller square that's b by b. That's our b squared. And what's left? 2 identical rectangles, and each one has an area of a times b. Put it all together, and you get a squared plus 2ab plus b squared. It's not just a formula anymore. It's literally the blueprint for this square.
Okay, so we've gone from a line to a square. The next logical step has to be a cube, right? So what does a plus b cubed look like in 3 dimensions?
You guessed it. If a plus b squared was the area of a square, then a plus b cubed has to be the volume of a cube. And just like our square, this cube isn't just one solid thing. It's actually built from 8 separate individual pieces. You can see them all laid out right here.
So what are these 8 blocks? Well, first we have 2 actual cubes, a big one with a volume of a cubed and a little one with a volume of b cubed. Then we have 2 sets of 3 identical blocks. There are 3 flat, squarish ones, each with a volume of a squared times b, and 3 long, skinny ones with a volume of a times b squared. You add up all 8 of those volumes, and what do you get? A cubed plus 3a squared b plus 3ab squared plus b cubed, the whole thing.
Now for the fun part. Let's see how they all fit together. We'll start with that big a cubed block as our base. And as we start slotting the other pieces around it, you can totally see how they're all designed to just perfectly interlock.
With each new block, the larger cube really starts to come into focus. Every piece fills in another part of the volume, pushing the sides out further and further, until they reach that full a plus b length.
Almost there! Just a few final pieces to lock into place, and they'll complete the faces of the cube.
And there it is, a perfect cube, with sides of length a plus b, built from our 8 little blocks. This is it. This is the physical, 3-dimensional form of that algebraic formula. It's an equation you can literally hold in your hands.
So, we've seen the formula in 1 dimension, 2 dimensions, and 3 dimensions. We went from a line to a square to a cube. But what happens next?
And this is where things get tricky, right? Our ability to visualize things just kind of hits a wall. I definitely can't build a 4-dimensional hypercube out of blocks on my desk. So how in the world do we figure out the formula for a plus b to the 4th power, or the 5th, or any power if we can't build the model anymore?
Well, it turns out the answer isn't a more complicated shape. It's a simple, incredibly powerful pattern that was hiding in plain sight the whole time. The blueprint for all of these formulas comes from a very famous structure in math, Pascal's triangle.
Let's just look at the pattern for a second. The numbers out in front of each term in our formulas, those are called coefficients. For our square, we needed 1 a squared piece, 2 ab pieces, and 1 b squared piece. So the coefficients are 1, 2, 1. For our cube, we needed 1 a cubed, 3 of one type of block, 3 of another, and 1 b cubed. So the coefficients are 1, 3, 3, 1. Ringing any bells? Those are exactly the rows of Pascal's triangle. This amazing pattern is the key. It tells us without a doubt that for a plus b to the fourth power, the coefficients are going to be 1, 4, 6, 4, 1, even if we can never hope to actually build the shape.
And that kind of brings us to this really cool conclusion. We started off just trying to see a formula, and we ended up uncovering this deep, beautiful pattern that connects geometry and algebra. It just goes to show you that sometimes the goal isn't just about finding the right answer. It's about appreciating the incredible, elegant structure that was hiding there all along.